I'm asked to say something to keep us from dying of boredom. Did you see the picture? I'm not going to talk about Java now while we're waiting for the projector to work, hopefully. Did you see the picture that was the background, the screensaver on my laptop? It's a picture of my son on a climb that we did in the Cairngorms, which is what we call a mountain range near to where I live in Scotland. So the picture looks very nice, and it looks like quite a nice day. The climb was quite easy, and we got onto the top. And the Cairngorms, this range of hills, is notorious in Scotland for its bad weather. You might think that the bad weather that we could get in Scotland would be nothing because you live in Russia, but I can actually tell you that on top there we had conditions which I have never encountered before, and I have been on mountains a bit. So it's really Arctic. It really is literally Arctic conditions. So there's a total whiteout. You couldn't see anything at all. You actually literally couldn't see the ground under your feet. And there's the snow, what we call spindrift, the snow blowing in your face, and it's quite a high wind, and it's very cold, and it's really quite intimidating, quite frightening situation. But we were all right because even though it's extremely difficult to navigate in those circumstances, I had the phone with me. So the iPhone has a GPS on it, and therefore you can always find out where you are. It's absolutely invaluable in these conditions, except that it doesn't work in low temperatures. So it thinks that its battery has run out. So from time to time I would put it in my pocket, and luckily I had yes, this is it. So we're back in business. So I'll finish my story quickly. So luckily I had a battery booster with me, and luckily when the phone wasn't working at all, we had a map and a compass as well. So I felt we really needed these things. And the thing that I found out that is my sole contribution to human knowledge, I think this is an original discovery, is that, as you know, these phones work on capacitance, and therefore the only way you can actually get them to work, you can't use them with gloves on. You can't use these phones if you've got gloves on, and it's a really cold day, and if I take my gloves off to switch the phone on, then my hands freeze, and the gloves were too tight and I couldn't get the gloves back on again. And this was getting to be really difficult, and there's no way of operating the phone without taking the gloves off. So I made a discovery, and this will probably be my only lasting legacy to human knowledge. You can work one of these things with your tongue. There you are. If you take away one piece of knowledge from today's conference, let it be that. Right, let's see whether we can go then. So, collections after 8. There's a bit of overlap between this talk. First of all, I should say thank you very much, even after you heard me this morning, for coming along again to hear me this afternoon. That's amazing, and I really appreciate it. So there's a bit of overlap between the talk this morning and this afternoon's talk. So I'll go quite quickly over some of the slides and spend a bit more time on others. I know that what you want to do is to move on from what I said this morning. So this is one slide that obviously that I don't need to spend any time on because we've done this. So my equivalent joke to this morning's joke with Rip Van Winkle is the question about why everyone, that means Clojure and Ruby programmers, are so rude about us. And they really are amazingly rude about us. They say things like 90% of all Java programs are written by morons. They say things like, if Java had true garbage collection, most programs would delete themselves on execution. These, by the way, these are all quotes that I found on people's blogs and in comments on the web. They say, lambdas aren't a new invention, even COBOL had them. That one I had to correct quite a lot of spelling errors in that. They say, I like this, sufficiently advanced Java is indistinguishable from satire. And of course they say Java is the new COBOL. So my theme today is how can we stop them from being so rude from being so scornful about us, from saying that Java is this old language. So you know from this morning what the answer is going to be, but I quite like the stories. I started off this morning or rather I finished this morning showing some code which I propose is the reason why they are so rude about us, because we write code like this, and it's my code, so I can say that. So the idea of this particular piece of code, I can describe it very quickly. It looks complicated, but there isn't that much to it. The idea of this code is that we've got these things. It's taken from a project of mine a while back, a personal planner. So for organising your time. So the idea of a plan is that it's a kind of a burst of activity. I'm going to spend 2 hours tomorrow preparing a talk for JPoint, and that's a plan. And sometimes, and I want to schedule these plans so that I can fit them all into my time schedule before and respect deadlines as well. I mean, there's no point in producing a schedule which has me preparing this talk in 2 weeks' time, because that's the only time that could be scheduled. So in this little bit of code, what I'm doing is I've got a method here called check plan, and what that does is, if you supply it with a plan that you're trying to schedule, it will ensure that it can be scheduled within its deadline. And if it can't be scheduled, then what it does is it returns back the problem plan, the one that was getting in the way, some other plan that was stopping it from being scheduled within its deadline. So that's really all that's happening. And basically what we're doing is we're getting a list of plans that have deadlines, and we are then iterating over it and checking to see whether it can be scheduled, and if it can't be scheduled, then a problem plan's returned, and in that case we break out of the loop and return the plan that's caused the trouble. So you know obviously what I'm going to be doing with this, because we were there this morning. Could we improve our image? Instead of writing that, we're going to write that instead. And I mentioned this morning. Now I can say a little bit more detail what's going on here. It's very much the same code. What we're doing is we're taking the deadline plans, and I'll talk about streams in a little while. But basically, we're taking those and we're mapping each one of these to the result of calling check plan. So now we've got a stream of plans which are problem plans. We want to filter, mostly we'll be getting back nulls from this. This stream will be full of nulls. So we want to check for one that's non-null, and if we can do, we find the first, and that's what we return. And once you know this API, clearly you'd need to be able to read these calls of map and filter and find first and so on in the way that I just did. But once you know that API, then my proposition is that this is a lot easier to read and a lot more elegant, and as we know from this morning as well, much more parallel friendly than the old version. So I'm going to be talking today about how do we get there. And you know as well, because this morning I mentioned what the magic ingredient, the so-called magic ingredient is, and the magic ingredient is, of course, abstraction over behaviors. Taking values to a higher order. That does sound quite magical. So the idea is going to be that instead of supplying values to specific library methods, like in this case we've got a rather specialized library method. This is an existing library method on collection. It's remove all, and you supply it with another collection, and what it does is it removes from the receiver, it removes all the elements that the receiver contains that are also found in the supplied collection. So it's okay, but it's very, very specialized. You can't remove any elements that don't satisfy that particular condition of being in another collection. You can't remove all the elements that are bigger than 3, or that have a non-null duration, or anything like that. You can't generalize it. They've got to be in a collection. So it's quite narrow. Instead, we're going to supply behavior to general library methods. So we're going to have a remove all method on collection, which is going to remove every element from the collection that satisfies a predicate. A predicate is just a function that returns a Boolean value. So you supply an element to this predicate, and it will return either true or false. And if it returns true, then it will be removed. Then the remove all method will remove it from the collection, and if it returns false, then it won't. So this is obviously internal iteration, the way I described it this morning. And this method as well is going to be on the collection interface in Java 8. So my obvious the idea of supplying behavior is these higher order values, which is the way functional programmers talk about them. But I just like to think about abstraction, about supplying behavior, little bits of code. We're quite familiar with the idea of doing that because anonymous inner classes do that. Every time you supply a runnable, which is something that's now quite traditional in Java, then essentially this is what you're doing, but this is a very much neater way of doing the same thing. So, predicate is an interface with a single abstract Boolean valued method. We've seen this. Oh, and the method is called test, and that doesn't matter. So that's quite important. We don't need to know what the method is called, and I'll explain that in a moment. I guess you may know the answer, but it's worth looking at it. Remove all executes test for each element. If test returns true, remove all removes that element. And there's something here which, again, you probably know about, but maybe would have made you sort of jump, is that I'm saying that in Java 8 we're going to have this new remove all method which takes a predicate. It's going to be on the collection interface, and you might say, well, hang on a moment, you can't just arbitrarily add new methods to an interface, because of course that's going to break all existing code, which is because the existing implementations have to have already supplied that method. So we're going to, in Java 8, as you may know, there's going to be a new way of supplying methods to interfaces. It's called default methods, and from now on you're going to be able to add concrete methods to interfaces, so that if the class that's implementing them has an implementation, in this case of remove all, if you wrote a new implementation of the collection interface that contained a remove all method that took a predicate, it would override the default method. But if you don't have one, so in other words, you've just got an old implementation of collection, then when collection is extended with this new default method, remove all taking a predicate, then the one that's embedded in the interface is the one that will be used. So this is a way of allowing libraries to evolve in a way that they've been held back from doing before, because we just really need these interfaces to be able to do more for us. If you think about the internal iteration that I was talking about this morning, I wanted a for each method, for example, on lists. How could you do that if you couldn't extend the list interface? So this is a big break with Java tradition. But it's been thought out fairly carefully, and it's not actually, everyone thinks, oh, multiple inheritance. And although I'm not going to go into it here, it actually turns out not to be a problem. We haven't got multiple, we do now have multiple inheritance of behavior, but the thing that people really get worked up about, and that really causes the problems, is multiple inheritance of state, and we still don't have that. So I don't want to talk about that much more. What I want to do is I want to talk about lambdas. So I got distracted there, and what I really wanted to say was, in this slide that I had here, what I'm wanting to do is supply behavior. That's right. So I want to supply behavior to a method like there. And it's going to have to be an instance of that interface, right? So how do we do that? And the answer is, of course, well, we know very well how to do that. We supply an anonymous inner class. We've been doing this for ages. That's how you make an interface instance. So here we've got an instance of predicate, which is just formed by declaring a new anonymous inner class here and overriding the only abstract method that predicate has on it. But this is really horrible. I mean, we've got used to it, but if you remember what you thought when you first saw this anonymous inner class syntax, I don't know what. I remember what I thought when I saw it. I remember particularly looking at these brackets at the end here, thinking, that really looks horrible. I mean, you get used to it, because you can get used to anything. But it's certainly not at all elegant, and it's really clumsy. And if we're going to have to do a lot of passing behavior around, having to write this kind of thing every time will really hold us up. We won't want to do it. The code's going to look very clumsy, and it's going to be difficult to read. And that's a very important consideration. And what's more, it makes people be rude about us. So and actually the interesting thing is that they've found that with applying a lot of clever inference, type inference, that actually you don't need all that stuff. Look, why do we have to say we're supplying a predicate? After all, if this is a well-formed method call, then we know that remove all takes a predicate. Why don't we assume that the expression that's being supplied there is an implementation of predicate? If it isn't, then things won't work. But it's easy for the compiler. It actually is easy for the compiler to infer that it's an implementation of predicate being offered. So we could actually just do without that. And if it comes to that, why do we have to say that we're implementing test? The method called test is the only abstract method on the interface. If we made a convention that said that any time we use an interface instance and we don't say what the method is, what method we want to call, and of course if that interface only has a single method, then the compiler should just assume I'm just going to use that abstract method. Or I'm going to take what you're supplying as an implementation of that abstract method. So we can do without that as well. We don't need to talk about that. And actually, if it comes to that, why do we have to say the type parameter is plan? Because if you look at it, then we know that a plan list is a list of plans, is a list of plan. And so in fact, the only thing that could be being supplied as the parameter to test here is a member of that list, which is a plan. So the compiler should be able to infer that as well, and it often can. I mean, this type inference isn't perfect, and sometimes when you're working with lambdas, you're kind of scratching your head and trying to figure out how can I help the compiler. But a lot of the time, the compiler gets it right. So we actually don't need to have that either. Oh, we shouldn't need to have it. There it goes. And if it's an expression, and we know that we're wanting to return, and we know that all that we want to do is return a value, again, in certain circumstances, we can do without the return keyword too. So all of this stuff is just boilerplate. We actually didn't need it, and it really made the program difficult to read and clumsy and cluttered, and it made all those people say those rude things about us. Actually, that's all that we need. We need a bit more syntax because we've got to put in the separator between the parameter list and the lambda body. That's that, and that's our lambda. Okay, it's not always as simple as that. Sometimes we have to help the compiler's type inference. If there's sometimes we have to put the parameters in the parameter list in brackets if there's more than one of them, or if we have to state the types explicitly. But in principle, that's what a lambda is. So that's what we're going to be supplying. Now you saw that this morning, so that's not very surprising to you. I guess you know it already. But it's quite interesting, I think, to see that really what we're doing. I mean, one way of looking at it, though this is not the right way of looking at it, is to say that lambdas are a better syntax for anonymous inner classes. Actually, the right thing to say is they are at least better syntax for anonymous inner classes. So you quite often get this, there's a kind of idea going around which I see on Stack Overflow all the time and have to kind of fight back, which is that lambdas are only anonymous inner classes with a better syntax, and they're not. In fact, there's much more than that to them. But even if that was all that they were, that would be a big step forward. Okay, so that's the idea of that's how we come to this syntax for supplying behaviors. Essentially, you can look on it as just a method call, very, very cut down, with all of the unnecessary boilerplate taken away. In this presentation, what I'm going to do is I've kind of introduced it, and I'm going to talk about the better APIs that I referred to this morning. Internal iteration I covered quite a lot. Pipes and filters. I'm going to talk about streams, which I ended up with on this morning, and maybe give a bit more insight into those and give some examples. And I'll talk about composing behaviors, how we can kind of make behaviors work together Because now we've got this idea of behaviors as something we can manipulate. Up until now, the only things we could manipulate or work with, the only first-class citizens in Java were essentially objects. Everything was an object. But if we now start thinking about behaviors, or functions, if you like that, if we start thinking about those as first-class citizens, we think about operations on those. And that actually gives us some interesting results. And then the parallelism thing you've kind of seen, but I've got a bit more insight into that. Okay, so internal iteration is pretty straightforward. I think you've seen that. The client has... I didn't go into detail this morning about quite how difficult external iteration is. I just said from the point of view of the collection, it stops the collection from doing its job. Actually, from the point of view of the client, it's really quite difficult because there's this kind of interplay going on. You have to say, do you have any more elements? And if you have more elements, then give me another element. And it's backwards and forwards between the control is distributed between the client and the library, and in a way that's not really very clean. The loop is, of course, inherently sequential. That was my point this morning. And the client would have to manage parallelism. It's not going to happen. So with internal iteration, we have this idea of supplying behavior to general library methods. And you saw that we could have something like a for each method. We added I told you this morning about a for each method, which had been added to a collection, which allows us to pass a behavior to that, and internally the collection will do its iteration, and the library controls it, can use its own iteration tactics, and so on. So that's the idea of internal iteration. A quick revision from this morning. Now I want to talk a bit more about how we got to having these streams in there. The idea of pipes and filters, the pattern of pipes and filters, is really a long-standing one. It was actually invented in 1970s, I think, and it was used in the context of Unix for the first part. And anybody who's been a power user of Unix or a system administrator will be pretty used to constructing pipelines like this that you see at the top there. And the idea of this is that we're going to pass lines of text from one process to another. So PS-EF creates the process table, and it passes line by line. It passes it through to the next, what Unix calls a filter, which actually in this case really is a filter. It's a filter in the Java sense as well, and that will drop all of the lines of text that don't contain the string login, and then this filter cuts out everything except the first 50 characters, so it takes a block of text at the beginning of the line, and then this one gives you the first 10 lines. So this idea of small programs that and each one of these things is a very focused purpose, and the idea of the pipeline is it assembles them together into making a special purpose tool from these small general purpose components. And it's turned out to be very, very successful, and people sometimes call it the Unix tool building philosophy. And this kind of philosophy is a kind of elaborate word to apply to a piece of computing, but computing science. But it has worked very well, and the idea has gone over into other fields as well. So in enterprise integration patterns, you see the same kind of general idea. We've got in this case, we're not talking about lines of text. We're talking about a Java object. And in this case, instead of passing the connector between them is now a pipe, which is essentially it's like a Java messaging queue, and an order comes in, and a filter will decrypt it, and another filter, using it in the Unix term, using the word in the Unix sense, will authenticate it, and another one will deduplicate the orders, and then they'll be dumped into a repository of clean orders. So this general idea has actually worked really well over the years. The advantages of this pattern, the reason it's worked so well is because the pattern has got some big advantages. There are no intermediate variables. When we do this PS-EF and pipe it into grep, we don't have to create an intermediate file to hold the process table before we pass it on. And that means we don't have to allocate storage for it. A single line is handled by each process in turn, and there's no overhead to that. In the case of what we're thinking of here, which is like piping the result of collection operations, from through filters in this kind of way, that's possibly quite a big advantage, because the intermediate storage that you might require if you created, as I did this morning, a collection which was operated on and passed to another collection. If those are very big, then there's a big overhead in terms of memory. That's going to put a stress on your garbage collector, possibly even lead to out of memory errors. So not having intermediate variables is a really good thing. Not having intermediate storage, is the same thing. Lazy evaluation is potentially a very good thing. If we actually find out, after we've collected 5 results, at the end of the pipeline, or in this case 10 results at the end of the pipeline, that's enough, then we don't actually need to generate anything more. So potentially there are big efficiency savings there. And there's this idea of flexible tool building that I mentioned. The Unix mantra, the slogan is, write programs that do one thing well. That's these little programs here. And then write programs to work together. So this idea has been very powerful, and it's been taken over into the idea of into the collections API in Java 8 pretty effectively. So here's the filter that I started off with at the beginning of this talk and the end of the last one, where it's got the map in it, it's got the filter, and it's got the find first at the end. So I called it a filter, but that's a pipeline. Here's a picture of the pipeline. Now, not the same diagram as I showed before, which had collections and connected by operations to other collections, Something different here. What we've got a source here, which is going to be, in this case, it's going to be the list of the deadline plans, and that gets turned into a stream. And stream is this big new idea in the collections API, and it gets transformed by various intermediate operations. And an intermediate operation is one which takes a stream and produces another stream from it. And at the end we have a terminal operation which kind of obviously ends the pipeline. So the assignment of the various components of that pipeline to their roles there is shown by these arrows, and the things that we plug into the intermediate operations and into the terminal operations sometimes will be lambdas typically. So check plan P to check plan P is a lambda, and we can put that into, that's actually a map operation. And the particular behavior the map operation takes a function like this from a P to some other type. In this case, as it happens, it's also a plan. It takes a plan and produces another plan, and that's what map does. And we're plugging it into the map operation here. We're plugging that particular behavior in, and in this case, we're going to plug into this filter operation. We're going to plug in that particular filter, the one that returns true if the supplied plan is non-null. So that's an instance of a predicate plan. So these the things that we're plugging in there are these interfaces, instances of these interfaces, like function and predicate, which are in the new package Java util function. And these are the only thing that's special about these. Well, the thing that's special about them is that the language team has spent a lot of time scratching their heads over getting them right. But the only thing that makes the only qualification that they need to be used in this context is that they should have only a single abstract method. Sometimes they're called single abstract method interfaces, SAM interfaces. So, but if you want to, quite often you'll actually want to use the ones that are already supplied. I don't anticipate that people will be writing very many of these SAM interfaces for themselves. So I still really haven't kind of boiled down the idea of the question of what exactly a stream is. Essentially, the idea of one of these operations is that the idea of the stream here is, you can think of it as being represented by an operation together with its upstream, and I'll talk about that a bit more in a moment. So did we manage to fulfill the Unix slogan? Have we written programs that do one thing well? Well, we've written programs that do one thing. This interface function here, as an example, has got a single method on it. All that it does, all that a function does, is it just applies itself to a t. A function is parameterized on 2 types, and all that a function does is it just applies itself to a t and produces an r. So typically you'll give it a lambda, and that's what it'll do. Predicate, same, tests. All it does is it just tests on the value. So it does look like they're pretty specialized, and we've got this basic idea of building them up that I talked about. So the question that I found myself asking when I was looking at this and trying to work out what was going on was, you don't see, and I think other people ask themselves this as well, because you don't often see it explained in a lot of detail, is what exactly is a stream? So a stream is I've seen different definitions. So this is my definition of it, is that it's a sequence of values. That's not very helpful in itself. The key thing about it is that it may be partially evaluated. You don't necessarily know at any given time what all the values in the stream are going to be. In fact, it's likely that you don't. They may be produced from a collection, as I've been showing you, but they might be produced from a generator function. They might, and in fact, they might be produced. This generator function might actually be infinite. So it may be that that the stream will never be totally evaluated. So how does that work? I mean, clearly the essence of that has got to be lazy evaluation. You can't have an eagerly evaluated infinite structure. So the idea is that the intermediate operations are all lazy. That is to say, they don't do any more evaluation than they need to. And the execution of these lazy operations, and lazy here is actually the same thing as saying intermediate operation. It sets the pipeline up, but it doesn't actually do anything in order to pass any values down it. So here instead of adding the terminal operation on the end, I've just said there's plan stream, there's deadline plans.stream. So a collection has to be kind of primed to go into a stream, and then I've set up the map function. And in, I think, in the next, oh no, it doesn't work that way. Then there's going to be a filter function. That's the filter function as well. But no values, the whole thing's set up, but no values have actually been passed down there. So I tried in this code here, is the code for Java util stream library is actually really quite difficult to understand. So I've tried to give a really simplified picture of how I imagine that it's working. I'm thinking that the way that what's happening here is we've got what's going to go into this box here is going to be something like an iterator, which will take an upstream iterator and the function that it's going to work on. This is particularly for a mapping function. And when it gets asked for its next element, what it will do is it will ask its upstream component for its next element, and then it'll apply the mapping function to it, and that's what it'll return to its downstream element. So you can see how the laziness comes in here. It's like the laziness that iterators have. It doesn't provide a value until it's asked for a value. And that goes in there, and of course it keeps a reference to its upstream, and here's the filter, which is actually even harder to write. This is really a tough one. But what I said was that if you ask for the next one here, then it gets the next one from its upstream, does the test on it, and if it passes the test, then it returns P. And otherwise it just skips it and goes on to the next one. This code is not by any means foolproof, so I don't suggest you look at it too closely. But the idea is there as to how one of these things would be plugged into a filter operation. And the key thing to notice about this is we've set this thing up, and now we've got the filter on the end there, and there's no evaluation yet. So how does the evaluation take place? The evaluation of the stream, the generation of the values happens when they are pulled down by the eager operation at the end. That's a terminal operation here. So in this case, the find first operation will pull values down. It'll call next on the on its upstream element repeatedly until it finds one, and when it actually finds one, then it'll return, and that it'll give up at that point. No more values will be generated. So there's potentially, obviously, there's big efficiency here in two ways. One, because you aren't going to get the elements. One, because you aren't going to get unnecessary elements produced. And one because also because this code is going to be produced in a form that the just-in-time compiler will be able to optimize much more easily than the kind of thing that I put up at the beginning. So that's the intention of the idea of this. I put the big blue arrow on the bottom to show the data being pulled over by the eager operation at the end. So we've got some stream methods. There's loads of methods on stream, which you'd have to go away and look at the API documentation. And I don't really recommend you do that unless you've got a special interest in Lambda, because this part of Project Lambda is still evolving. There's quite a lot of changes even now. We've seen some of them. So filter returns a stream of T. It's a lazy operation, obviously. And the interface it uses is predicate, and the signature of the lambda that has to be supplied is a T to Boolean. That's obviously what the test method essentially does. Map changes each element of the stream into something new, and the interface there is function from T. If it's a stream of T, then it's going to produce an R for each element and return a stream of R. And so that's the lambda signature for the that we're going to have to supply to the map function, to the map operation, is a T to R, and so on. So that's sorted as lazy, even though you think it wouldn't be, but it's lazy in the same sense as these others are, that it doesn't actually force evaluation. By contrast, reduce, which we've seen, find first and for each, these are eager, and in each one of them, reduce, for example, the one that I showed you this morning with the plus signs, that takes two T's and it produces a T. And in the case this morning, they were all ints. T was T is an int. Find first, obviously, is a predicate on T. It just has to find something that satisfies its predicate. And for each has a lambda signature there, has a void, because it just actually, from T to void, because it just works on the on each element, and then it doesn't return anything. So it doesn't sort of really fit in that well with the overall thrust of this, which is all about immutable data. For each is kind of uneasy there. Here's some examples of application of some of these lazy methods. So I'm imagining filtering my plans. A plan has a duration, which all you need to know. I could get all the plans from the stream that are longer than 15 minutes by filtering over a predicate from P to its duration being longer than 15 minutes. That's Joda time. That's a Joda time interface. You could get the durations of the plans, a stream of the durations of the plans by mapping each plan to its duration. You get the first 10 plans with limit and all but the first 10 plans with skip. One of those has changed its name. That's right. Skip is now substream. That's the new one, substream. So I need to update that slide. And here I've taken those same 4 examples, and I've completed the pipeline by adding some terminal operations on the end. So here I've said I'm going to take this stream of plans that are longer than 15 minutes, and I want to collect them I want to dump them in a collection at the end. So I've got a collect method here, and there's a method called collectors.toList. It's a kind of, the collectors are a way of as the name implies, taking the values of a stream and collecting them by some means, and some of the means that are quite elaborate. So you can transform them in the process of collecting them into a collection. I've decided to get the duration of all the plans in the list. There's a different version of reduce. This is one that has a reduction base, duration.0, and then adds them all together like that. Pretty much like the plus, pretty much like addition of arithmetic before. Are the first plans all longer than 15 minutes, where you call all match on that predicate? And here's a particularly stupid one. Count the plans after skipping the first 10. So I was just looking for an example there. Not obviously very practical. Okay, so right. The last, I've got 2 more sections. So, but I'm short of time because of our problems at the beginning.
You have 7 minutes maximum.
Okay, right. So one of the, my claim has been that besides this, the improvements to the collections API, that we've got improvements to other APIs as well. So here's an example of how this idea of abstraction over behaviours, of passing behaviours around, actually gets us much nicer results than we had before. So you may have seen this because Brian Getz has used this in examples before, but I really like it, and I think I've got a kind of good way of explaining it. Normally, if we want to sort a list, we use a comparator, and you've seen, everyone has done this. You defined an anonymous inner class implementation of comparator in this kind of way. So a plan is, in this case, a plan has a task that it's associated with, and I'm saying that I want the ordering on plans to match the ordering on the task that they're associated with. Well, that's horrible. Right? So one thing that we could do, which would be nicer, would be to replace that with a lambda, because I've been saying anonymous inner classes have a better syntax now in lambdas. But the problem is actually, even if we did that, there's still a problem, which is that compare is monolithic. The method is monolithic. There's 2 things going on there. It's getting a field from the thing to be compared, and then it's doing the comparison. And those are 2 different tasks. Now, with lambdas, and once we start thinking about behaviors as things we can manipulate, then we would say, we really don't want to have to do this thing we don't want to have to combine these together in one monolithic thing. I mean, what, for example, if we wanted to change the key that we were comparing on? Well, you can see that in this comparator there, you'd have to go through and you'd have to look for every occurrence of get task, and you'd have to replace it. So it's copied, so it'd be a search and replace. Not very nice. Not very nice. Even in this tiny example, it's not very nice. What we'd really like to do is we'd like to parameterize compare on the key extractor, and we can do that now very easily with our new ideas. Seem to have skipped a double. All right. Okay. So what we're going to do is we're going to factor out. We can factor out the key extractor here, the get task here. Let's call that. We'll give that a name. We'll call it. We'll call this because it's a behavior. And we can now abstract over behaviors, and we can call that task getter. How about that? So task getter is a function from plan to task, and it takes a p and it gets the task from it. And what we get now is, if we substitute that into this top expression, we get task getter.apply p1 compared to task getter.apply p2. And you're thinking this isn't actually this hasn't achieved very much, but hold on. So that's what we've done. What we now can do is we can factor out the task getter. Okay, still on the same thing. We can now parameterize on the key extractor. And in fact, we don't even need to think about how to do that, because this is going to be common enough that there's a library class, a library method that does this. In Java util comparators, there is already a comparing method has been supplied that does exactly this. So the comparing method takes a key extractor, and it returns you the comparator that would have used. So this method accepts a behavior, the key extraction, and it returns a behavior, the made-up comparator. So task getter, that horrible thing that I was saying you didn't like very much at the end of the last slide, now boils down to this. This is if you like, a factory method for that takes a key extractor and does comparison via natural ordering on it. And now we have a comparator out of that. And this gives us some quite nice results, because we can compose fine-grained methods. I mean, we can fine-tune behaviors. For example, here we can say, supposing now if we want to change the key that we're comparing on, we can do that really simply. By task and by duration are defined really neatly, because we're parameterized on the behavior of the key extractor. We can combine them. We can say I want to sort the list by task as the primary key, and then subsequently by duration. And even better, with the new syntax and with the sort method that now appears on collection, we can say plan list.sort by task, then comparing by duration. And this is a lot more readable than what we had before. I mean, we've really come a long way from that anonymous inner class definition. Okay, 1 minute to go. So I talked about parallelism before, and I'm not going to. We're short on time, so I won't go over these slides in detail. The point about these slides, where I talk about concurrent hash map, is the one that I made earlier when I said that the library writers are in a very good position to do divide and conquer, because they know the recursive structure of their own data. And the reason I put these slides up was not because I expected you to understand this code, but to show you really I mean, this is actually a very simplified version of the code in concurrent hash map that does the work of divide and conquer. So here, for example, we've got the compute method, which actually applies the task that we've asked to be done recursively, and it's generated. What it does is the compute method. If you look here, this is the kind of the key line here. There's for each value task, I should have said, for each value task is a kind of package of work, which is going to be like the intermediate nodes on the tree this morning, where I said, well, let's just sum up the values of the array. Well, for each value task is going to in a concurrent hash map, for each value task is going to work over a set of values. And how's it going to do that? Well, the answer is it's going to divide them up, and it's going to create a new for each value task for half of them, and it's going to fork that off. So that means giving that to another thread to be executed, and then it's going to do the action that it's supposed to do on the other half. So it's done that division, and it's passed half of it off to a new thread. It's kept the other half for execution in its own thread, and that will be repeatedly done until it gets down to a small enough section that can be done serially. So that's the kind of essence of it, as you see in that slide. And the picture that I have that I get from this, and the one that I would want you to take away with, is this idea that by putting what we have to do, if we want a stream to behave in a parallel way, we have to instead of saying we want a stream, we say plan list.parallel stream instead of stream. And what we get then is something like what I showed earlier, but this time I want to show it in kind of more of a kind of physical reality. The data structure is forked, and then it's forked again, or the processing is forked and then it's forked again. And when it gets down to a small enough data set that it can be performed serially, then the pipeline is executed, right? And the terminal operation then. The results of the terminal operation are finally combined. Now this is a big deal, because what this actually means is, this is the way that I said that the collections library writers could internally parallelize their work. Because what you're seeing here is that this is being done on a single thread. It's a task that's being done on a single thread that can potentially as well actually have what's called loop fusion done on it. They're all the operations in the pipeline are rammed together into a single loop. And the JVM is increasingly over time going to be in a position to understand and to optimize that code. So potentially this picture here is going to be one where we're going to be able to make use of the massively parallel hardware that's coming down the line. And that is one of the two motivations. I hope in this talk I've kind of really fleshed out a little bit the claims I made this morning for lambdas. The two claims are more readable code, better code, code that's nearer to the intention of the developer, and code that's more parallel friendly. And those, and I hope in the two halves of this talk I managed to show this. So once again, lambdas seem like a small syntactic change, but they're going to be a big difference in the way that we're going to be programming in Java, particularly in the collections libraries, but elsewhere as well. For resources, I obviously am going to recommend. It's pretty obvious where I'm going to point you, and I believe there's a good book coming out sometime. And that's it. And I'm afraid we're out of time for questions. I think. Sorry about that. I'd be very happy to take questions offline.
Yes, thank you very much. It was very interesting. I think we have time only for 2 questions.
Oh, we do have time.
So,
why didn't they introduce the function types? You mentioned the special class function that takes one parameter and produces one result. And what about the 3 parameters?
Speak into the microphone.
It's okay. It's okay. Why didn't they introduce function types? That's really the question. Why have we got these things which kind of fit fairly uneasily into the existing Java type system? The answer to that question is because we don't have reification. Erased generics just represent too much of a problem for the introduction of function types. So the long-term program is reification. Probably not in Java 9, but in Java 10, I'm imagining. And then after that, the way that lambdas have been defined has they've been very careful not to exclude the possibility of introducing function types in the future. That's why I say lambdas are much more than just, or potentially much more than just anonymous inner classes. So they've left that option open, but it can't be done at the moment because of the way that generics were implemented.
Maybe I didn't understand right, but talking about the first example, when we had a loop over collection of items, and then we made some suitable element about plan and breaked cycle. And then we replaced it by lambda, yes? Mm-hmm. We have a chain of different functions, map, filter, etc. Mm-hmm. But when we have a call of map, we have to iterate over all the elements. Yes? Mm-hmm. But it's less optimized than first example, when we have no functional methods.
I think you would. If the question is why do we have to iterate over all of them, then the answer is well, possibly we don't. I mean, I'm not quite sure the example. If I'm right in thinking that the example you're talking about is the one that has find first as a terminal operation, then for that the internal iteration will not go over all the elements. It will go over as many elements as are required before find first can actually finds an element. So it's not necessarily the case that the idea of lazy evaluation is that only as many elements will be required, will be produced as are required by the terminal operation.
It will optimize all the chain, yes?
Yeah, absolutely, yeah.